Good morning, good afternoon, good evening, wherever you are in the world, and welcome to the first official lesson of the Physics 101 course by your host, Ade Aylan, Dr. Ade Aylan from Aylan Academy. Now, it's taken me quite a while, quite a couple of runs to record this video, but I'm here now. And I think what the standard is going to be is that I'm already going to have some laid out notes, and all I'm going to do is annotate over the core notes, and that saves me wasting a lot of time or spending a lot of time actually writing during the actual lesson. Okay, now this is week 2, lesson 1, and we're going to be basically creating a little foundation for ourselves as physicists. So the main aim of today's lesson is to talk about units, to talk about vectors, to talk about the core, the things that underpin how we talk to each other as physicists. So when we give each other values, like you're a physicist, I'm a physicist. When I give you a value, it often needs to come with some form of unit, because if I just give you a value, you're not going to know what the hell I'm talking about. So when given a number in physics, it must generally be quoted with a unit, and quantities without units are almost always meaningless. So for example, if I give you a unit of 10 energy, you're going to know, okay, 10 energy, right? Well, not 10 energy. If I just say 10 joules, you're going to know that it's 10 units of this particular quantity, which is energy, right? So generally how much, energy comes in different forms. So, but here we are actually going to talk about energy in terms of prefixes, okay? Prefixes. So I'm just going to get my pen out here. Sorry about that. I'm going to get my pen out there and expand again. So we're actually going to talk about prefixes, okay? So prefixes are what comes before the unit that tells you the standard, the scientific notation of that unit, or exactly how much. The reason being is because if I was to tell you, okay, I have 10 million units of energy, right? And you have to write that down. You don't always want to write down 10 million every single time, okay? Because that gets tedious after a while. You can use prefixes, unit prefixes, in order to simplify this into an easier way. So there's 10, and then there are 6 zeros after that 10. In physics, that would be a mega. Okay, so that's right here. So I'll come here and write 10 megajoules, right? So this is the same thing as 10 megajoules. Or if I wanted to be fancy with my standard notation, my scientific powers of 10 notation, I could write 10 times 10 to the 6 joules. They all mean the same thing, but prefixes enable us to write units much more simpler. And what I have here are a table of units. Again, 10 for everything. So 10 joules, 10 millijoules, 10 megajoules, 10 picojoules, gigajoules, etc., etc. And next to those notations in blue, I have exactly what the number is in standard form. And I have a couple of examples here. If I was to go, maybe not pico, because that's too many zeros, but let's do 2 more examples. So megajoules, we've already done that, but I'll write it out again. So it's literally 10 followed by 6 zeros. 5, 6, and we write the joule there. And you can also write that as 10 times 10 to the 6 joules. And then down here, if we go to picojoules, so 10 pj, pico is a very small amount. So that is going to be 1 0 before the decimal place, followed by, it should be 11 more. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And then we write the 10. And that is 10 picojoules written as a long ass number. But we can also simplify that by writing 10 times 10 to the minus 12 joules, okay? So that is how you quote units to each other. We also need to talk about the differences between scalar and vector quantities, right? So energy is a type of quantity, and it would be a scalar quantity because it just has size. It just has an amount. energy doesn't have a direction. You don't say, "Oh, I got energy coming in this direction or going in that direction." You just tell someone the size of the energy. The same thing with temperature. The same thing with weight. I can weigh anywhere between 95 and 98 kilos generally. I don't tell you the direction of my weight. Distance and speed. Distance is how far you've moved from a point. Okay, and even if you go back to that point, it's the total distance of how far you've moved, walked, ran, sped, whatever. Speed, how fast you're moving. Now vectors are slightly different. Vectors have both size and direction. Okay, you've got the size of the vector and you've got the orientation of the vector also. Common vector quantities are magnetic fields, or fields in general, gravitational fields, magnetic fields. You've got forces, you've got acceleration. The counterpart to distance and speed are displacement and velocity. Displacement is how far you've moved with respect to a fixed origin. You can move towards it, you can move away from it, you can go around in a circle, but if you go back to the way you came from, just for the fact you've gone around in a circle, your total displacement would be zero, because you know, after the time has elapsed, and we look at the total displacement of where you've moved, you haven't moved anywhere. You may have moved a certain distance, but displacement, how far you are at the end of your journey compared to the beginning, has not changed. Velocity as well. So speed is just the size. Velocity is now the direction. Okay. So here's an example of an actual vector. So in physics, we no longer use Cartesian X, Y, Z axis. We use IJK for our notation. And yes, we still use Cartesian axis. So Cartesian is a fancy name for just saying, a 3D box. So forwards, backwards, up, down, left, right. That's a Cartesian coordinate system. We use the notation IJK. Here, I have an example of a 2D vector in I and J, where I is the horizontal direction, and J is the vertical direction. So this red line here is a vector that is written as 6 3s. Now I've written it a bit lazily there, and I'm going to write it again as 6 3 like this. Okay, this simply means I've gone 6 in the horizontal direction and 3 in the vertical direction. And in green, I can also notate that. So I moved 6 in the horizontal direction, the positive horizontal direction, and I've moved 3 in the positive vertical direction. And that gives me a resultant vector, the red one, right? And we're going to find out what this resultant vector is. Because vectors not just have size, vectors not just have direction, but they have size / magnitude. And to find the magnitude, exactly how long a vector is, we use Pythagorean theorem, okay? So Pythagoras' theorem. I wonder if this would look neat if I just, no, it's not going to look messy. So I guess what I'll do, I'll just underline it in purple like this. So I'll need to find a scheme where I'm boxing equations and I'm underlining keywords, or I'm writing keywords in a certain color, but I'll figure that out as we go along. So we're simply using Pythagoras' theorem to find the resultant vector, the magnitude of a vector, not resultant, the magnitude of a vector, how long a vector actually is based upon its components, right? So here, that's just going to be the horizontal side squared plus the vertical side squared, and then all square rooted to find the horizontal. So if we've gone 6 in horizontal to find the magnitude. So if we've gone 6 in the horizontal, we square that, we get 36. If we've gone 3 in the vertical, we square that, we get 9. 36 plus 9 added together, that's 45. We square root, that's the square root of 45. And all I've used is the law of surds. All I've used now is the law of surds to basically show that the magnitude of the vector is going to be 3 root 5. Okay, that's the magnitude, that's the total size of the vector. All right. Now, what if you are given the magnitude of a vector already and you are told to resolve that vector into its base components? Okay. Well, we can use trigonometry. So remember back in high school, middle school, SOHCAHTOA, silly old Henry couldn't advance his troops over Africa. Well, we can use trigonometry in order to decompose the magnitude of a vector into its horizontal and vertical components. So if we orientate a vector like this, then the horizontal is always going to be the adjacent. This is always going to be the adjacent to the angle. Okay, so everything with respect to the angle, and then the vertical is always going to be the opposite to the angle. And we just choose which one. We just choose which identity we want to use in order to decompose this 5 newtons into its vertical and horizontal components. And all it is, if I want to find the horizontal, I need to work out what the adjacent is. Because I don't know the opposite, we can't use tan. But because I know the hypotenuse, which is the longer side, which is, the magnitude, and I know the angle, I can use cos. I can use the cos relationship. And all I'm going to do is that I'm going to rearrange this cos relationship. So first of all, we have cos theta equals A over H. I rearrange that to make A the subject, and I've got the adjacent equals H cos theta. I plug in the values. I've got 5 newtons as H. I've got 20 as the angle, and it's going to be 5 cos 20. The adjacent has to be 4.70 to 2 decimal place. Now, if I wanted to find out what the opposite was, assuming we still don't know the adjacent, we would use sine in this case. So sine for the vertical composition of the vector. So now, last but not least, we need to know that vectors can be added and subtracted. If you had 2 forces, so let's just call this force 1, and let's just call this force 2. And let's say that force 1 and force 2 are acting on the same object. What is the resultant force? What is the total force that the object feels? What is the total force on the object? Well, all it is that the total force, so F total is just going to be equal to F1 plus F2. Now, in vector notation, that is going to be 3, 5 plus 5, 3. You add the i's, you add the j's, and that is going to be 8 over 8. Okay, so we have a vector that is 8 across and 8 up. And we can show this easily by simply dragging this vector and putting it along there. And you can clearly see that, had I drawn my axis neatly, you can clearly see that this is approximately 8 across and 8 up, okay? So we get a total resultant vector of 8 across and 8 up. And that is simply how you are able to add vectors. You can also subtract vectors as well. So if you, for example, if you wanted to find out, let me backtrack on this. If you say wanted to find out this vector here, like what that vector there would be. Now this is a little bit esoteric, but this actually comes from vector subtraction. So what you can do, okay, is that you can displace F1 and put it over here and make a dummy vector here. And you could basically say, hey, I've traveled along 5, 3, and I've gone, so if I was to flip the direction of this, and I've gone the opposite, I've gone -3 and -5 in this direction. So let me put negatives here. What is what is the resultant vector, or what is the said pathway. The reason why we can do that is because this dashed vector is the same orientation as this solid line vector. So all it is in this case is that F total, or I'm going to write F resultant, is going to be equal to F2 take away F1, and all that is going to be 5, 3 take away 3, 5, and the resultant is going to be 2 minus 2. And you can clearly see that this looks like I've gone 2 across and negative 2 down as my resultant. So 2 across and negative 2 down. All right. I'm going to stop the video there because I've spoken enough. But this, believe it or not, basically creates a foundation for us to move on to the other topics. I will write this note up a little bit neatly, especially with the extra example that I put there, and I will upload it to the website. But I hope you've learned a lot in this very short video, and I'll see you in the next one.